Hey gents, I wanted to share with you some data that I collected using a mass on a spring and having one of our motion sensors sit underneath it. I let it oscillate for a bit and then I asked the little brain to do a curve fit. The curve fit that seemed to fit best was a sine curve fit, and so you can see up here, this was essentially the shape of the data where this would be the vertical position and this would be time. And this curve fit data that came back was this, and it followed this form. The x position was equal to the a, or the amplitude. Sine of b was the constant in here with the horizontal axis t. Notice it's to the negative first value, so this is 1 over seconds. And this RMSE is the root mean square error. And essentially what that does is if there is a difference between a perfect sine curve and the actual data point. So if the data point was sitting right here, the error would be the vertical distance between the two. It would take that vertical distance, square it to take away, so you didn't have negative values canceling out error of positive values, so they squared it to take away the negative values that would be down here. Sum them all together, take the root of all that, so take the squaredness out of it, and so what you're left with is how different by the vertical distance is your data, how different is it from a perfect sine curve. So the ideal number would be what's sitting out here in front right here, 0, and as you look, it's pretty much 0. So the motion, the up and down motion of a mass on a spring oscillating pretty much perfectly fit sine curve, and the sine graph that was perfectly fit would follow this form. Now, one of the things we can figure out, if you'll notice, here's a T2 value where that data point is at the peak of that part, and a T1 value, which is the time for the peak of that. If I take the difference of T2 minus T1, what do I have? But I have the time from peak to peak, also known as the period. And so T2 was 3.3 seconds, T1 was 1.62 seconds, so I have 1.68 seconds is the period. So armed with that information, that kind of starts to beg, what does this B mean out here? And then since B has a unit of 1 over seconds, the possible relationship would be, since we have a period in seconds, would be some constant over the period t. So if I run with that assumption that this constant B out front is something over the period, if I solve for C using this value right here, I notice I get 6.367, which is about a little bit less than 2% of the 2 pi value. So what that means is the very likely relationship between, I don't know why I have to do this to have it move for me, but I do. The very likely relationship is that B is 2 pi over t. Now, since we know relationship between period and frequency is 1 over t, another way that I could write B is 2 pi times frequency. And since we know that the period is 1.68 seconds, I can figure out what the period is, and it comes out to be about 0.60 hertz. So if you imagine in class the mass bobbing up and down on that spring that we had up in front, a little bit less than twice per second, a little bit smaller frequency than 1 hertz seems pretty reasonable. So what we can conclude from this is a general equation that we can use for the position of the mass, or the end of the spring, if you like. The position for that, x, is going to be equal to the amplitude of the oscillation and times the sine of 2 pi over the period times what time do you want to know where we are. Or another way to write it would be the amplitude times sine times 2 pi times the frequency of the time of, hey, when do you want to know where we are? There you have it.